It'll be appreciated if you can switch on your videos.
Yes, please.
All right. Good evening, everyone. Welcome to this session on quantum computing by Qiskit Fall Fest 2022 in collaboration with Developer Student Club, TIET. Today, we have with us Elena. She is a quantum software engineer at IBM Research and has multidisciplinary engineering background with experience in fields like machine learning, deep learning, robotics, virtual reality, and quantum computing. Elena, over to you now.
Okay, thank you. All right. So, well, I was asked to come here and speak today. The idea, I think, is to maybe give you some motivation for this mid-checkpoint. I believe there are some challenges coming up afterwards in the week, or?
Yes.
So you went through the initial training, and now you have some challenges, right?
Yes. We do have 3 of them.
Okay, nice. Cool. So yeah, and I thought it would be a nice opportunity to come here and I guess share a bit my story with you. Mainly because the reason why I ended up in quantum computing is because I was involved in these kind of events and challenges. So I think this is a great way to start. And yeah, I wanted to kind of encourage you to continue in the field. So I have a presentation. I have some slides that I can share. It's actually a bit reused from another event, but I think it can be relevant. So if you're interested in listening to it, I can, I guess, open my presentation.
Yes, that would be really interesting.
Okay. You will see some suspicious dates because, of course, we didn't make it for today, but sure work out. Okay. Can you see my screen?
Yes.
So you see this, how to build a career in quantum?
Yes, yes, we can.
So, yep, my presentation that I did actually doesn't have a date, perfect. This presentation that I gave a couple of weeks ago was focused on how to build a career in quantum. And it's basically based around my personal story. And yeah, I thought it would be cool to go through it again here. So if you guys have any questions, you're free to let me know at any point. I don't really pretend to be here just speaking, and yeah, I would like to have some interaction. So please, at any moment, I mean, this is not any formal presentation or anything. So feel super free to ask me any questions. Let's start from what do I do now. So I am, as you presented really well, a quantum applications software engineer, I guess. I work on Qiskit. I'm pretty sure you guys are already familiar with Qiskit. And I, in particular, develop the applications modules from Qiskit. So these are the ones I mentioned here. It's Qiskit Nature, Terra Optimization, Finance, and Machine Learning. I think it's pretty cool that we are even placed in the IBM Quantum Roadmap. I don't know if you have ever seen this, but IBM every year, roughly, publishes a plan of what the future of quantum is expected to be from the IBM point of view, and this is called the roadmap. And we are in a really cool point because we're in this point where the hardware is already developed enough so that we can start playing around with higher levels of the stack. So this would be the kernel development, algorithm development, or model development. And I work at, let's say, the algorithm development level, which in a short way is I develop Qiskit application modules. Yeah. So this is a short introduction of what I do. And now I'm also going to do a short introduction of how I got there. Well, it all started in Spain. I'm going to go a bit fast through this because I don't want you guys. This is my home university in Madrid, Spain. And I started studying engineering. So my bachelor's was in something called industrial engineering in Spain that internationally is more like general engineering. I specialized in automation and electronics. So this was robotics. And I started doing some research internships in my lab, in one of the labs in my university. This one was a field robotics lab. So I did my bachelor's thesis there. And then I continued, let's say, concatenating research internships. I did a couple of them. And I was working on many different fields. I was working on virtual reality. I was working on adaptive interfaces and also with the robots themselves. And I continued with a master's degree in the same field. And after a bunch of years working on field robotics, I thought, okay, I believe that I am done with robots. What I kind of really liked about my job, not my job, my, let's say, tasks or projects was the artificial intelligence, machine learning, predicting part. So I decided to specialize and study a master's degree in computer science with a specialty in machine learning. Now, the fun part, I guess, of the story is that I didn't study it in Spain, but I actually moved to Japan. So I just wanted some adventure. I had the opportunity to go to a fairly good Japanese university with a scholarship. So I thought, why not? And in 2018, I moved to Japan. This was a really cool experience. I have, I guess, lots of pictures here and some ramen. And when I was in Japan, I studied in a computer science, computer vision lab. I focused on 3D pose recognition, 2D to 3D pose recognition, and I developed deep learning architectures for that. And this was still really cool, but while I was in my Japanese university, I came upon a hackathon. So it was called Qiskit Camp Asia 2019. This was before COVID, so it was in person. And it's when I really came into contact with what quantum computing was. I hadn't heard of quantum computing before that hackathon. And I joined there with zero hopes that anything would come out of that, because of course I barely knew what quantum computing was. And something that I discovered during this hackathon was that, let's say, the quantum computing field is actually in need of people with my expertise, or let's say with a more traditional computer science background. Let's say the quantum computing field is actually composed of several subfields, right? So traditionally people come from a physics background and they either specialize in like experimental physics or a more theoretical physics, quantum information theory and stuff like that. But then we're coming to a point where if we actually want, let's say, to develop useful applications of quantum computing, we need to start introducing the software development component to it. And there are not that many people that have a, let's say, good software development, good software engineering basis, and they also understand the basics of quantum computing. And this is why IBM as a whole and Qiskit, the whole Qiskit team, is so involved with their community. This is why there are so many opportunities to learn online and to kind of train, because we basically need people that are able to deal with these tools properly. So anyway, this is a bit of background, but I joined the hackathon. I ended up being second. I really enjoyed the experience. And from there, I decided, I want to learn quantum computing. So I started learning online. I started looking into Qiskit tutorials. I started looking into other hackathons. At that point, it was already the beginning of COVID, so I had a lot of opportunities that were fully online, which for me was an advantage because I was living in Japan and I wouldn't be able to go in person to all of these events that were in the US or in Europe. But I mean, I could still join from my home. So that was also a nice coincidence, I guess, or something good we can get out of this terrible thing that happened. But yeah, I joined a lot of quantum computing events, a lot of networking events, and I was also just studying by myself. In the meantime, I was working. So I started working in a machine learning startup, and I was, let's say, continuing my normal path as a software engineer, but I still had this idea of quantum in mind. And at some point I was spending more time in learning about quantum computing by myself than in my actual job, or let's say mind time. So I thought, okay, why not? I am actually going to study this for real. So last year I started studying while working, a master's degree in quantum computing technology. And I did this again remotely because of the new, let's say, distributed remote world we're living in. And I focused on quantum machine learning because it was, let's say, the point of connection with my previous background. And while I was studying this master's, I got the chance to do an internship at IBM Research. So I applied for this internship position. It was a bit strange because I had been working before, but in the end, they agreed that it would be interesting to have me as an intern. So I focused on integration between PyTorch, the machine learning library, and Qiskit runtime. And through that internship, I ended up collaborating a lot with the team in Zurich. And again, we kind of realized that there is actually a space for people that have a more traditional, let's say, classical development background. And that is kind of how I ended up in my current job. So now I'm working in Zurich, Switzerland. I started not even a year ago. And I have a chance to interact with all of these super cool quantum researchers and also super cool developers. And well, of course, I really enjoy it. I think it's a really cool place to be in at a really interesting time. And yeah, this is pretty much my story. And this was the part of the presentation that I wanted to share. In this presentation, I also kind of had a final wrap up where I extracted some takeaways that I kind of thought that would be interesting. I am, again, talking all the time from my personal experience, so I cannot, promise that this is the road to success. But I think it's always interesting to share and hear these things from people that have been there. So the first takeaway is that quantum is a very multidisciplinary field. I already said it, and in this kind of field, you actually need multidisciplinary people. And this means that there are multiple paths that can take you to, let's say, the end of building a career in quantum. However, I think it's important to remember that all of the paths involve work. So the fact that you can, let's say, enter the quantum computing field from a computer science background doesn't mean that you will, let's say, escape from learning at least some minimal notions of quantum physics. And the other way around, like there are some, researchers that they just studied a PhD and they have this, let's say, traditional physics research background, and they're like, oh, I'm just focusing on writing papers and I will never ever write any code. The truth is, if you want to stay in academia, it's fine. But if you want to, let's say, be more involved in industry, at some point you're probably going to have to write code, even if it's just for running your own experiments. So yeah, everything is connected. It's, of course, you get people that are experts in one of those fields, but let's say the whole machine works because of the interconnection between them. So you, I guess, never stop learning, which is something that happens in many other jobs too. And then another takeaway I had from my path was that getting involved is a really great way to learn. So nowadays we cannot really predict where quantum computing is going to go. So we have, for example, at IBM, we have this great roadmap that has a very concise and like precise prediction of what's going to happen for the next, let's say, 5 years. But what's beyond that is still to be, let's say, determined. So I personally would say that the fact that we don't know what's going to happen doesn't mean that this is not still a cool thing to work on. I think it is. I think there's a lot of potential, and I think that the more you get like involved, the more you join events, the more you interact with other people that are also interested in it. You do challenges like these ones you're doing this week. You kind of get you start filling in the puzzle. You start connecting the pieces of the puzzle, and you start also realizing where do you fit better into this puzzle. So for me, getting involved was like a great way to, first of all, decide that I wanted to have a career in quantum, because this was not clear. It was not like my lifelong dream or anything. I was supposed to have a career in machine learning. And so it helps you to see where you fit. And it also helps, of course, the people from the company side to assess your skills, right? So we all know this. It's super nice to say I've participated in this and that. But I would also remember the first part. So it really does help you see where you can contribute the best. So yeah, you combine all of these things, you put them into a mixer, and then you turn into an expert. Super easy. This was the presentation I had before, but let me I wanted to add a few like personal. I didn't want to exactly repeat what I said last time. The reason why I'm here today is I know Peña from the Qiskit Advocate Mentorship Program. So I would like to do a little bit of advertisement here and say that if you think that these things you've been looking at this week are cool, you can become a Qiskit advocate. There are lots of instructions online. You can find, I believe, one or multiple blog posts. You can follow Qiskit, I think, on any social network they have, which is, I think, Twitter. You can follow Qiskit on Twitter. You can follow it on LinkedIn. And, it's relatively, I think, achievable. You will have to pass a developer exam, but there's also a lot of material to prepare that. So something to think about if you like this. There's an incoming challenge from Qiskit also. Like I think it's coming up in November that you guys can look up. I don't have the link right now. What a disaster! But you can look it up. It should be easy to find the IBM Quantum Challenge. Those challenges are really good. I've participated, I think, in all of them except for the last one, the one from last spring. And yeah, I would really recommend them. I think they're super fun. And this year's challenge is focused on Qiskit runtime, and the runtime primitives, which is, let's say, the new way that Qiskit wants to let people access quantum computers, and it's supposed to be a bit more encapsulated. It's supposed to be easier. So I think for people that are actually starting, it's even better to already come across these like cool abstractions that don't make you have to fight with all of the small details of what quantum computing is, because it can be a lot if you just need to deal with everything at once. So yeah, I would encourage you to try it out. And in general, just follow all the information that Qiskit offers. I mean, there are other companies too, and I'm not saying here, hey, join IBM. But of course, I am not an expert on what these other companies offers, but I know that there are good challenges too. Unitary Fund has a lot of stuff too. And yeah, again, I wanted, for example, to show internships, but because I am a developer, I don't have access to the precise information. I don't want to give out specific links that maybe will not work. But the cool thing is nowadays, really, everything is documented online. And I think if something, I guess the proof that you can be living in a complete different continent and somehow end up involved in things and actually move across the world to work. So, there's an example, at least one that I know of. And if you want to interact now, ask me anything.
Yes, thank you, Elena. That was interesting and insightful. What I'd love to know is, why did you choose Japan for your studies?
That's a really good question. I don't have everybody thinks, oh, the US, you really want to build a super cool career in tech. And I think it was my idea from the beginning to go to the US. But at some point, it was like, why do I have to do what everybody does? I don't know. I had a weird circuit there, and I thought, what other options do I have? And they're really cool, for example, universities in Europe. But because I am from Europe, I felt like this was too close. Or I thought, okay, I'm going to end up in Europe anyway. So I ended up finding Japan. And it's I would say, an underrated opportunity. Not as competitive as other places, and they have really good experience. Why not?
Makes sense. Also, as you mentioned, the 5-year plan for quantum, what do you think the future of quantum could be like?
Yeah, this is the tricky question. I think there are several possible futures. Right now, we are at this point where we need to kind of adjust the way we are making algorithms and kind of making things work to the current status of the hardware, right? So there's this 2 parallel tracks. And for example, there's a big, let's say, hype about error mitigation now. So the thing about error mitigation is that it allows you to work with, let's say, imperfect hardware, which is what we have. And it does give really good results. So do I think the future of quantum is error mitigation? Well, I mean, I would expect, there would be a point where the hardware is good enough that maybe we don't rely that much on this error mitigation techniques. But that's why everything goes hand in hand. So near future, I think error mitigation will be a super cool thing to implement and a super cool thing to have. And it will allow us to run already maybe things are close to having an advantage. But I cannot predict what comes next, so who knows?
Right, and that's the exciting part.
Yeah.
And what attracted you to quantum computing, since you've tried your hands at various other fields as well? What was it about quantum that attracted you to this?
Yeah. Well, I guess I've always liked physics. There's this component that's there, but I genuinely really like this idea of working in something that is being built at the moment, right? It's like, I don't know, there's this movie about the one that's called Hidden Figures, about this women that were working in NASA when they brought the first IBM computer. And, there were there were, of course, super smart people, but they were also in the right place at the right time. So I have this kind of feeling okay, we are at this time where we are developing this super cool new thing, and I just want to be there.
All right, that's interesting.
Yeah, but it's a mix. So it's also on, let's say, on a daily basis. It's really cool because I get to interact with researchers, I get to interact with developers, and I enjoy both of them. Some people that come from a super, let's say, traditional software background, they completely short circuit when they interact with researchers, because software engineering is, DevOps, very structured, very efficient, and research is the complete opposite. So you also need to know how to a bit switch between the two contexts or find points of interaction. Sometimes it's challenging, but I like the challenge.
Right. Also, people, you could go ahead if you want to ask any questions.
Yeah. If not, I can always just talk. It's one of my specialties. No, but really anything. That's, I guess, what I'm here for. It's your chance.
You could unmute or type it in the chat as well.
How's the day at work? So I go to the lab a lot. We have the option to work remotely, but I personally like being there. And something I really enjoy about working at IBM, I think, is the relaxed working culture. So of course, I mean, people are very committed to their job, but there's a lot of flexibility. So usually when I go work, I have a coffee. Then I work for the morning, then we all go together for lunch. In the evening, we maybe play some ping pong. And I interact a lot with the US. So my evening sometimes is like a bit delayed. Like I end up leaving a bit late because I need to have meetings and stuff with the US, but in general, it's totally fine. So yeah, very, very vague answer, but that's what I could come up with. I can go back to this one later. So can you tell about the roadmap from basics of quantum computing to attempting to become an expert in the field for a complete beginner? I can try. Let me share again, maybe my screen, so I can share this roadmap. Okay. So I'm imagining this question is like this video where explains something in a really easy way and then just gradually increases the level of difficulty. I don't know if I interpreted it wrong. But I can start with the easy part and then we can see. So this roadmap has, as you can see, 4 layers, right? The basic layer is the hardware. So this is what is explained here when it says system modularity. So all of the chips that are shown here in different squares will correspond to a different quantum chip layout. So we are in 2022, and so far we have developed 3 new layouts. Well, I don't work on the hardware side, but I'm going to say we. All of them have bird names, by the way. So kookaburra, for example, or flamingo, condor, they're all birds. I think kookaburra is an Australian bird because our J. gambetta is Australian. So I think that's why. So anyway, as you can see, these chips are built from little like bricks, and the more we progress through the roadmap, the smaller the bricks are. This just represents the amount of qubits that fit into a chip. So there's something important that we need to know, and it's that we cannot just build infinitely large chips. There's a limit, and we can see this here on Condor. So you can see that from Falcon to Condor, the chips just get increasingly large, and they can just fit more qubits into them. But at some point, you reach this limit of like the actual machines you use to build the chips, and then you're like, okay, what can we do? And then it turns into building these connections between chips, and these like extremely efficient, fast connections. And there are actually several like types of connections, and these are what are shown in flamingo, kookaburra, and then that is like one type of connection. And then you have on the bottom heron and crossbill, where you have these other types of like either longer interactions or like very kind of stitchy interactions in crossbill. So these are just like different ways of building out chips. So the thing is, well, in principle, the more qubits we have, the better, right? The cool thing about having these like chips that you can connect to each other is that it really helps scaling. So ideally, to have like a cool quantum application, we would need something in the range of maybe 10,000 qubits. And in order to reach that, which is something that is still not within the roadmap, you need to have these connections. So these are just things that are, of course, exploratory. So we have the longer range ones, the shorter range ones, we have these cross-stitch ones, and I guess there are many more. I cannot explain this at an expert level because this is as far as I think my knowledge goes, right? Then on top of that, so on top of the quantum hardware, you have what's called the kernel development. So kernel development is close to firmware. It's like an intermediate layer. So these are, let's say, the different tools that algorithm developers can use later. These are, for example, things like circuits, the idea of a circuit and how you program it, and then how people can access it, and how can they set values to the qubits, and how can they measure. All of these things are what's circuits. Then you can see from 2021, there's this other word called Qiskit runtime, which is all around the IBM news lately. Qiskit runtime, what it let's say, yeah, the idea that it expresses is that you have your local computer that you program, and then you have a quantum processing unit that is somewhere around the world, and you need to communicate with this. So this communication is done through circuit jobs. This means you send a circuit to the quantum computer executes the circuit, and then they send you back the result. And this job-based model has some, let's say, shortcomings. So when you have many people, many jobs, it is very difficult to kind of manage things so that you will receive all of your jobs within a reasonable time. And Qiskit runtime, what it provides is a new execution model where you have these ideas of sessions and, let's say, ways of grouping jobs that you can send to the quantum processing unit so that you can, in short, just receive your results faster. But all this interaction between the local classical computer and the quantum computer is what is covered by Qiskit runtime. Within these communications, you have concepts like primitives. I don't think I can get into that now. And dynamic circuits, and like smaller components that basically either allow you to execute circuits or allow you to, find different ways of communicating with the backend. There are other words here like error suppression mitigation, which is error suppression and mitigation, and error correction, which is something that, so the difference between error suppression and error correction is that we all know quantum computers are noisy, and they're noisy by, let's say, by design. It is impossible to have a noiseless quantum computer. You can have a quantum computer that only has a specific type of noise. And if that specific type of noise is controllable, then you can error correct it, and you can virtually work with the computer as if it was noisy. This is let's say, the goal of error correction. But unfortunately, right now, we don't only have that specific type of noise, but we also have other noises. We have a lot of noises. We have noise that comes from the qubit, noise that comes from the gates, noise that comes from these connections between the circuits. Everything just injects more noise. So error suppression and mitigation, what it tries is to control all of these other noises that will not lead you to an error-free use of the computer, but it can get you close, or let's say it can make it a bit more manageable. And yeah, then on top of that, so once you have, let's say, the basic tools to access quantum computers from your classical computer, then you can just forget that you're using a quantum computer, and then you can just think about building algorithms. So this is what is done at the algorithm development layer. And this is what people that, for example, study quantum information theory end up doing. So they just, they write a paper, they think of an algorithm, and then they go use the tools from the kernel developers to actually run an experiment with them. And these algorithms can be applied algorithms, so they can be, specific solutions to specific problems in certain fields. So that's why here they say machine learning, natural science, optimization and such. There are already a lot of algorithms published, and a lot of algorithms are part of Qiskit. So when you're using the library, you can, you don't have to write your own algorithm and access the circuits and connect with Qiskit runtime and all of these things. You can just forget about those layers, and you can just call an algorithm and say, hey, here's my data, run, give me back the result. Now, in the future, this quantum serverless idea is to be able to have not only QPUs, so not only quantum computers, quantum processing units, but also be able to combine them with classical CPUs, with GPUs, and just have this kind of idea of having a lot of computational resources that you can use for your problem. The same way, or in a similar way, you now can use, AWS. You can just, deploy some pods to do some machine learning tasks. The idea is to, in the future, have people, not know anything about the quantum layer going on underneath, and they just call a quantum computer to execute some kind of task, and it will all happen in a, let's say, seamless way. So this is what quantum serverless means. And then on top of that, you have these prototype quantum software applications, which are the applications. I hope this is a bit self-explanatory. So yeah, this is, I would say this is the explanation of what the roadmap is.
That is so cool. Thank you. People, feel free to shoot in more questions if you have any.
There are more. Okay. There's one more. Yeah. How can you tell about the field of quantum artificial intelligence and the ways you can get in? All right. I guess what's generally used, the term is generally used is quantum machine learning, but quantum AI also exists as an idea. There are two ways of getting in. One of them is, let's say, let's keep in mind that quantum computing is an exploratory technology, and this means that there are no actual applications happening right now, right? So you can right now be a machine learning engineer and you can work, I don't know, in autonomous cars or something, but there are no quantum autonomous cars yet. So if you want to get into quantum machine learning, you need to do it through either going into the theory behind machine learning. So actually understanding learning, let's say more mathematical part of it. In the end, machine learning is very based on statistics. So, building up your knowledge on that direction, then it will be very easy to kind of transfer it to the quantum realm, and you can maybe do some research that is connecting very fundamental machine learning research with quantum. And another alternative, I guess, is to try to approach it a bit from the applications point of view, but as I said, you don't have autonomous quantum cars. So the way you can do that is through also theory. So what you can do is you can have something like you want to solve a quantum chemistry problem, and you want to apply some machine learning methods for it, and you want to see if having some native quantum machine learning methods are even better than just having machine learning, right? So this idea is usually explained as quantum algorithms for quantum data. So it's like, okay, I have a problem that is quantum and I want to solve it. So what kind of models I can use, what kind of algorithms I can use for solving this? Both of these, let's say, fields are, I would say, pretty theoretical. But it all depends on how the roadmap goes. If the roadmap reaches a point where you can actually run, decent quantum neural networks, then I think the field is going to change a lot, because then the field will become a bit more based on experiments, the way actual machine learning research is done. So, in machine learning research, usually you design a neural network and then you just train it with a data set, and then you benchmark and you compare, is this accuracy good? Is this accuracy bad? This is something that you can do to a certain extent now with quantum, but it's only to a certain extent. So, you cannot really compare quantum neural network that can only work with 3 qubits, because you only have 3 qubits to run it, to a classical neural network that has like 6,000 layers and 5 million parameters. Like, I mean, you can compare them, but the result is really not going to take you anywhere, right? So we have this mismatch in the way classical machine learning hardware is super well developed, and quantum machine learning hardware is like in its baby stages. So I personally think that, doing benchmarking is not like an interesting use of time because of this mismatch. I mean, if you find something you can benchmark, then you're like a genius. Like, you get the Nobel Prize. But in the meantime, I think it's very important to go through the theoretical side. So That being said, if you just want to understand and get an idea of how quantum machine learning works, there is Qiskit machine learning, and there are some nice tutorials that we are improving, right, with Sanya. So if you can, if you want to check them out, this should give you an idea of what can be done at the moment.
I think that is what the most exciting part about the field is. That it is at such a nascent stage of research, and there's tons of things that we can explore.
Mm-hmm. I mean, yeah, I agree. I think it's fun. Mm-hmm. Yep.
Feel free to shoot in any more questions, people. All right. Also, as mentioned earlier and informed in the previous workshop, we have 3 challenges going on right now. If I may share my screen.
I am not sharing anymore, right? Yes. Okay.
Let's have a look at what these challenges are. All you need to do is successfully submit a pull request on GitHub repo by 21st October end of day. And you stand a chance to win an IBM swag kit. So the first challenge is that you need to design a quantum circuit that acts as a biased coin. You could use any percentages, as in the example it's mentioned 60% of the time it should be heads or zeros, and 40% of the time it could be tails. And you can set the bias you like, and you can assume any missing information. A hint could be that you might have to use bone rule in this. Apart from that, challenge number 2 is you need to take a qubit and put it in state of 1. Create an equal superposition and present the measured result as a histogram. You need to explain the result obtained. We have 2 hints here. The first one being, if you think of a gate that transforms 0 to 1 and implement it. The second one could be, if you think of a gate that makes A equal to B and then implement it. Challenge number 3 is, you need to take 2 qubits and entangle them in as many ways as you can think of. You need to plot a histogram of the results, and you need to explain the results. The hints that we have here are, you could either think of a gate that entangles 2 qubits, or you could think of a gate that puts a qubit in an equal superposition and use these 2 gates to make a circuit. You could also think of different initial states of the qubit. Also, the most important hint being, you could Google it. So what you need to do is submit a pull request on GitHub repo of DSCTIT by 21st October end of day. I hope that is clear. If you have any questions, you might ask them. All right. Elena, would you like to add anything?
No, just good luck. These challenges sound cool. Maybe try them at home.
Yes.
See if I'm still fresh, remembering the basics of quantum.
All right. Thank you so much. It was a wonderful session.
You're welcome.
Thank you, Elena.
Thanks for joining. And yeah, good luck. If you ever want to contact me, there's an open Qiskit Slack channel. Mm-hmm. And my Slack handle is my name. So you can find me on the Qiskit Slack channel.
All right. Thank you so much.
You're welcome. I'm going to have to drop now because I have a meeting coming up in 10 minutes. But as I said, good luck. I hope you enjoyed the talk. And yeah, have a nice week, day.
Oh, thank you.
Bye.
Bye. Thank you for joining in, people.
You're welcome.